Hello, everybody. Welcome to Geology. Hope your week's going well. Let's go a little deeper, no pun intended, into tectonics. The last video, which you probably should watch first, dealt with what's going on the surface, like what's going on in this little wedge with the upper layers, crust, asthenosphere, all of that. Be a little familiar with that vocab before we go too deep here. Let's go down and think a little bit more about what's going on in the outer core and inner core down into the mantle. I'll come back up and chuck some notes on this at the end. But first, the question should be asked, how do we know any of this? The deepest drilling projects that have ever taken place, ones that have taken place over the course of decades, have made it a negligible amount down into the crust. Forget about getting down into the mantle and certainly into the cores. That's the stuff of science fiction. It's not going to happen. But I have the audacity to sit here and say to you that at these depths, the inside of the earth has these properties. So how have we figured that out? It's an important question. And I'll ask another question that kind of answers it. I had a science teacher once tell me that I had bones, that I have a whole bunch of bones inside of my body. Now, I've never seen any of these bones. I'm like, yeah, I can do that, and I can tell that there's something going on in there. But what evidence do I have for having bones inside of my body? Well, one time I pretended I knew what I was doing, trying to play roller hockey for a league in Syracuse, and went way too fast into the boards and banged my knee all up, which necessitated a trip to the hospital, where, as you can guess, you probably know what happens here. Some of you, I'm sure, have done it. They take a machine to shoot waves through my leg and see what comes out on the other side on a film and use that to see what's going on. And boom, there it is, an image of the bones that are inside my body that I can't see, that I have no intention of seeing anytime soon, right? They're in there, though. How is that the same as what we've been able to do here? With my leg, it's waves going through something, and whatever happens to them inside of that makes it look different on the other side. So we're going to do the same idea here. How can we get waves to go through this, come out on the other side looking a little different, but reveal on that trip what is going on the interior, on the not visible interior? And the waves we'll use for that are seismic waves, earthquake waves. And we've got them happening every day all over the place. Some more data could be gathered on this by you tomorrow if you really wanted to set your mind to it. When an earthquake takes place, it sends waves of energy through the planet. And what happens is a thing that you're maybe familiar with. If you've ever heard the term, and if you're a note taker, I'd pop it down. If you're just doing it in your head, note that is an important one. This thing happens called refraction. So it's easy to observe in these cases. If you've ever done put a straw into water and seen that it looks like it's bent or broken, but you pull it back out and it's one intact straw. If you go fishing and your line's in the water and you're looking at it, it looks like it bends at a weird angle, but it's not. There's tension on it and it's reasonably straight. Or if you're going to try to spearfish, you got to understand this principle too. That's what refraction is. What refraction refers to is the bending of waves. That's broadly the definition. Broadly and simply, right? Maybe too simply, but it'll work. It's really easy to picture in this scenario. We've got air, right? And we've got water, H2O. So when light travels, it's going the speed of light like in a vacuum, but when it enters when it enters things that it, yes, passes through, but that there's something there, like our atmosphere, it slows it down a little bit. And when it slows it down, the path gets bent. And then it slows it down further when it goes into thicker stuff, like water, right? So it can go faster through the air than it can through the water. And at that interface right there where the two meet, the result is that it's going to appear to bend. Same exact principle here. The straw's not bent. The light waves that get slowed down by the water bend at a specific angle. And you can figure that out with a thing called Snell's law. This is you got to do the angle and a little bit of light trigonometry. It's pretty easy stuff. We're not going to worry about it here. But it's a fairly easy thing to figure out if you have to do physics. Where it's a touch I don't know, cooler, a touch more interesting in the world of geology is that this is like from this density to this density, it happens, right? What we've got inside the Earth, though, is because of the pressure, we've got ever increasing densities as you work your way down. It gets to be more and more and more compact, right? It's got the overall overriding weight of everything above it on it. The density increases as you go down. Now, there's like layers, but you could also kind of picture it as a continuum. If every like X number of feet you go, the density goes up by X. The more closely packed those molecules are, the different ways in which they transmit those earthquake waves, you're going to get a more general bend to the wave as it goes. So it's a little more complicated than just the air, water, Snell's law thing, but principally it's kind of the same idea. A light wave bends as it enters a higher density. An earthquake wave bends as it enters a higher density. Only it can do so in many little steps as it goes. So what we've done then, all it takes is have an earthquake go off somewhere. Nature will do that for us. Track those waves as they bend their way through the different layers of the planets, record where they end up, and we have seismometers all over the place to pick these things up. And you got yourself basically kind of like the same principle as my x-ray on my knee. You end up with what, with a little bit of cleverness, can turn into an image of what's on the inside of the planets. And it reveals some cool things. One thing we're going to do a quick sneak preview of is this idea of P waves and S waves. This, except for these two diagrams, these are all just copied right out of the textbook. This one's copied out of the earthquakes chapter. We'll do this in better detail when we get to the earthquakes chapter, which is part of this segment of the course, but I don't want to make this video go too long. Let's stick to the nuts and bolts of this. So for now, just say, okay, I trust you. There's such a thing as a P wave out there, and there's such a thing as an S wave out there, pending the details later on. They travel in different ways as they go forward. And because that is a thing that we'll unpack, what happens is that we see different patterns with the way that these different types of waves travel through the planets. The way that a P wave goes through looks roughly like this. The way that an S wave goes through looks roughly like this. So what the heck is all this? What this has showed us is that these S waves, you notice, stop at the outer core. They get absorbed by it. They do not get transmitted through the outer core. So there's this S wave shadow zone, it's called, about 103 degrees away from the epicenter. And this is tricky to picture, but if you can take this two-dimensional diagram and turn it into a three-dimensional globe, what would that look like? 103 degrees, it's like a circle way down here, opposite the other side from the epicenter. Down there, no S waves whatsoever. So that made people say, okay, something fishy's going on with the outer core. We got to figure that out. P waves do manage to go through the outer core, but because of the way that they refract when they go through these different boundaries, or again, do that slight bend as they go through the continually increasing pressure as they go down, end up producing some kind of funky patterns and end up with a shadow zone of their own between 103 and about 150 degrees. And again, if you could picture this in a three-dimensional planet, that would look like a donut shape going around the bottom of the planet. Bottom being just opposite the epicenter. There's nothing special about this spot other than that's the spot where an earthquake happened to take place the day they were studying, right? So what does this show us? And that'll be, there's an extra blank page for you. That'll be how we really want to figure out what's going on. The outer core, I mean, this is right here. This is in your diagram. It has been determined is a liquid. So make a note of that. Liquid outer core. We know that, and again, we'll unpack waves a little bit more when we get to earthquakes. We know that because of by studying these kinds of waves and the way that they travel forward through a medium, they can't do that through liquids. They can do it through solids, even the mushy solids that we found up here in the asthenosphere that we've already talked about, but not through liquids. Doesn't work. and it's been what's revealed. That's how it's been revealed to us that we must be dealing with a liquid down there. And then because of the funky things that happen to the P waves over here, like S waves technically would go through the inner core, but they can't get to it because it's surrounded by the liquid outer core. But by the way that the P waves react in here, we have been able to figure out that that is a solid. Now, temperature also increases as you go down, as does pressure. And if you're thinking about that, it might feel a little funny because if the inner core is even hotter than the outer core and they're made from roughly the same stuff, why is it that that's a solid and that's a liquid? It's hotter. And the reason is whatever the freezing point is where you go from a liquid to a solid, right? Here's a water bottle. If I get this down to 0 right here in this room, it'll freeze. But all those numbers change if you put it under pressure or get rid of pressure. There's enough pressure on the materials there that it changes the freezing point, melting point enough that it's basically, if you want to think of it this way, it's essentially compressed into a solid, even though it's hotter than its surrounding liquid. But either way, that's how we've figured it out. That's going to be the big thing. Earthquake wave refraction has revealed that there is a liquid outer core, the solid inner core, and of course revealed what's going on with some of the stuff we talked about in the last little chunk with what's going on up in the upper surface. All right, one more thing we're going to throw in is this idea of convection. And I know I've mentioned this word before. If it's new to you or you forgot, convection is like the flow of a liquid or a gas caused by density differences and heat differences. The hot, less dense stuff rises, the cool, more dense stuff sinks. Well, this is going on in the outer core, probably not at that scale. That's just an example of convection. The outer core, it's churning like crazy, and it's got liquid iron in it. That, we have to think, is responsible for our magnetic field here on Earth. And as we get through the course, we're going to see that we really like having a magnetic field as humans that live on the surface. Induced, that's the right word, by convection and liquid. Say Fe for iron. Oh, sorry. Outer. All right, now we'll go a little bit more into that too. When we start talking about exactly how plates work, we got to think about how this has been unstable through the years. It's not perfect. Our North Pole, our geographic North Pole, if you have a globe, the metal bar that goes through it that spins around, and the magnetic North Pole are off by a little bit. And over long terms, constantly changing. And as it turns out, also sometimes flip-flopping, reversing polarity. So this is a pretty dynamic place with some wild stuff going on. It's been relatively stable over our short human history. Long term, there's been some significant changes. And we'll talk about that when we talk about mid-ocean ridges. But let's keep that in mind. I think that's pretty much all we'll do with the, I'll pop back to the textbook here with that inner core, outer core. But keep that in mind that's where our magnetic field comes from. So, I mean, don't ignore the textbook. Come on back to this. That's some good stuff there. And then I think the magnetic stuff was down here. Yeah, check this little section out too for how that works. Sound good? All right. Hope you have a good day. We'll talk to you soon.